Since we are projecting angles, horizontal angles, there are certain mathematical relationships that we can take advantage of. As this angle, these sides continue to diverge, this offers us some unique qualities to that behavior that allows us to have the ability to do certain measurements in the field that helps us with sampling. So this figure shows, for instance, that for each 1 inch increase in dBH, as we increase in diameter at breast height, 1 inch, this figure shows that for each 1 inch increase in dBH, for an angle of 114.18 minutes, that the sides are tangent to the tree at dBH for an increase of 2.75 feet in distance from the previous distance. So notice as we go from this size tree, 1 inch, to this size tree, that it is a distance of 2.75 feet from here to here, as the sides are tangent to the diameter of that tree, or to the area of that diameter, the circular area of that diameter, where the circles represent the cross-sectional area at breast height of each tree. Thus, all trees above are considered borderline trees. So a 1 inch tree is borderline for an angle of 114.18 minutes, is borderline exactly 2.75 feet. A 2 inch tree for that same angle is borderline an additional 2.75 feet, and a 3 inch tree is borderline an additional 2.75 feet from the 2 inch tree for that angle. And that's where we get the use of prisms without going too deep into the prisms. But a 3.03 diopter prism can be used to project a horizontal angle of 114.18 minutes from a vertex right here, located 4.5 feet vertically above a sample point. A 4.29 diopter prism can be used to project an angle of 147.34 minutes. A 7.44 diopter prism can be used to project an angle of 255.23 minutes, etc. So the relationships that we just discussed allow us then to get tables to help us check the limiting distance for borderline trees. Those trees whose imaginary plots are right on the edge of encompassing the point. And so we need to check them to make sure that we are correctly deciding whether the tree should be sampled or not. So when using horizontal point sampling, variable radius, often the projected angle is near tangent or tangent to both sides of the tree. A true borderline tree is one for which the distance from the sampling point equals the limiting distance, the true borderline tree. But often with the tools that we're using, they appear to be borderline, so we have to check them. Thus, the tree's imaginary plot intersects but does not encompass the sampling point. It kind of goes right through it. That's obviously very rare, and we don't, in the real world, everyone, we don't know if it's an exact borderline tree. We don't have the precision in our equipment. But it looks borderline enough within the tools that we're using that we need to check it with the tape to the best of our ability. So another way to state this is that a borderline tree is the maximum distance that it can be from the point and still be considered a sample tree. For true borderline trees, the sides of the horizontal angle are exactly tangent to the cross-sectional area of a tree at dBH. And since all instruments that project an angle are merely tools, okay, they're not, they're not the truth, okay, that are not highly precise, we need to use the mathematical derivations above, those tools associated with angles, in a sense, the properties of angles, to determine whether the tree should be sampled or not. Since each imaginary plot is assumed circular, correct, variable radius, and the area of a circle is dependent upon its radius, we can determine the limiting distance for any projected angle that we select, and the tree size, in this case diameter, okay. The limiting distance is a function of the tree dBH and the plot radius factor of any associated angle. That additional distance from the point at which, given the tree's diameter, the imaginary plot is barely touching or barely encompassing the point. So we can look at this table here. And so here we have our angles in diopters and angle size in millimeters, kind of what we've touched on. And these are associated, these angle sizes are associated with various spatial area factors. And we will touch on that shortly. You may have heard of a 10 BAF or a 20 BAF, or probably many of you have not heard of a 40 BAF because they don't use them very often around. Maybe a 5 BAF, but certainly a 10 I'm sure you've heard about, and probably some of you have heard of a 20. And then your angle size in diopters, which is used for prisms. Then your ratio between the dBH, the diameter, and the plot radius. And this then leads to the plot radius factor. That additional distance from the point to at which a tree's pith would force that tree, or would allow that tree to be called truly borderline, given its diameter. So for instance, if a dBH is 6 inches, okay, if a dBH is 6 inches, and let's say we're using a 30 BAF, all right, with a corresponding plot radius factor of 1.588, the limiting distance is 6 times 1.588, which is 9.5 feet. So for that 6-inch tree, any point that was 9.51 feet or more away from the center of that tree would not be sampled. If a point was exactly 9.5 feet away from that tree's center, that tree would be truly borderline, and it should be sampled. If a point was less than 9.5 feet from that tree's pith or center, it would be sampled. And this is where you get into, as I said, given the precision of the tools that we are using, most likely anywhere probably from, depending on the person too, anywhere from anytime the tree is 8.5 feet or more away from the point, you would probably need to check whether it was borderline. You probably could not tell for sure whether that tree was in. Now, some people may be very good at it, and they could maybe tell for sure, but those are kind of things where you get into borderline. As I said, it's going to depend a little bit on the conditions of the forest that you're working in. Is the tree complete? Is it truly circular? Remember, we are just assuming trees are circular, and often they are nearly circular, but many times they're not. They're a little oblong, and so that can create some problems determining whether it's in or not. So when in doubt, it's always best to use this table and to use your plot radius factor associated with the BAF that you select, given how you feel that BAF will help you obtain the information that you need to make your management decision to help you best meet your objective, your management objective. And that's what we're doing the inventory for, is to obtain information about the resource in a time, cost, and logistically efficient way. So we can basically see what I was just talking about. Here we have a tree. This is the diameter of the tree and the basal area cross section at 4.5 feet. And this tree has an imaginary plot. And this could be any particular BAF in any associated angle, right, in degrees, or angle size in millimeters, right, depending on the BAF that we would select. But this tree is truly borderline, okay? And we could think of it too like it's nearly border, right? It's right on the edge of the sample point, all right? Now, we would never know this, right? We're not actually drawing. We're not going to establish a true circle out in the field. That's where we use like a laser or a logger's tape, some tape to measure the distance from here to here. But we calculate mathematically what distance that should be, such that if that distance is less than that limiting distance, that tree would be considered sampled. So we can read that here, everyone. When conducting an operational inventory in the field for the tree depicted above, the tree's imaginary plot would be too close to the sampling point to definitively determine with any angle projection, the ruloscope, the prism, the jim-jim, the cruisall, an angle gauge, right, whether that tree should be sampled. So the green circle represents the tree's cross-sectional area, dBH. When measuring the dBH of that tree, and dependent on the angle selected, e.g. BAF, whether it be 10 or 20 BAF, for example, we can determine the limiting distance beyond which that tree's imaginary plot would not encompass the sampling point, and thus the tree would not be sampled. So, let's assume the tree above has a dBH of 10 inches, so it has a diameter of 10 inches, and that we are using a 10 BAF prism projecting an angle of 104.18 minutes. We know for this selected BAF that for each 1 inch of dBH, the limiting distance increases 2.75 feet. That tree can be 2.75 feet from the point and still be sampled. Thus, the limiting distance is 27.5 feet. 10 inches times 2.75 is 27.5 feet. Let's assume the tree is located 26.8 feet from the point. So you probably could not tell definitively with any one of the instruments, the prism, the jim-jim, an angle gauge, whether that tree was truly in or out. Thus it would be included in the sample, since its imaginary plot would encompass the sampling point. Okay, so at that distance from the point, it would probably be too hard to tell definitively with any of the instruments that we have whether it's in or out. So you'd have to measure the distance. You'd have to calculate the limiting distance based on the 10 BAF and the associated angle behind the math behind it. Knowing that the plot radius factor is 2.75, you'd multiply that by 10, okay, because it's a 10-inch tree, and then you would measure the distance from the point to the tree, or from the tree to the point, and then compare it to the limiting distance of 27.5 and see whether if it's equal to or less than 27.5, it should be included, and it is less, so therefore it should be sampled. Rules of thumb. On average, when a tree is plus or minus 5 feet from the limiting distance, it is difficult to determine with any of the instruments discussed above whether it should be included in the sample. Now that's just a rule of thumb. That's going to depend, as I said, on the conditions. What's the light? You have a little bit of slope or not? How many other trees are surrounding the tree? How easily can you see it? What's the shape of the cross section? Is it truly circular? Is it a little bit oblong? Etc. So here we have a table including the limiting distances for our 20 BAF. So we have our inches in dBH and then our tenths of inches. So 1.0, 1 inch tree, a 1.1 inch tree, a 1.2 inch tree, a 1.3 inch tree, an 8.0 inch tree, an 8.1 inch tree, an 8.2 inch tree, an 8.3 inch tree. What are the limiting distances for a 20 BAF prism? All right. So first we need to find what is the plot radius factor. And if we come over here and we look here, we have a 20 BAF and the plot radius factor is 1.944. So if we come here, instead of 2.75, that distance is what? That distance is 1.944, okay? And then you'll notice for a 1.0 inch tree, its limiting distance for the 20 BAF is what? 1.944, because that is 1 inch tree. So it can be that far away from the point and still be a borderline, be a true borderline tree and thus sampled. Multiply that by 2 and you get 3.888. Multiply that by 3 and you get 5.832. Basically the figure that we saw, that as you go along, the sides of the angles are diverging, and that leads to the borderline state for a particular diameter. And then you're going to add a slight amount of extra distance for the 1/10 of an inch. All right. So let's just say I had an 11.4 inch tree. What would be the limiting distance if I was using a 20 BAF? Well, if I could print this table off, because I can calculate it, right? Before I even go out to the field, this is kind of what we're talking about. I can determine the probability of sampling these trees. I can determine this table. I can create this table before I go out to the field. And it would, nowadays we have little, computers that will calculate it for you automatically. But 20 years ago, you wouldn't necessarily need to sit there with a calculator and type it up, right? If you knew you were going out to a 20 BAF, you were going out to a stand, you're going to use a 20 BAF or 10 BAF, you would just bring this table with you. And you could just, especially if it was dry enough, if it was raining, it was a little bit harder sometimes because the paper would always be getting wet, but you could just open up your tally folder and then just look at the limiting distances. So 11.4 would be 22.162. And I could calculate this before I go out to the field because I know the mathematics behind it. All right. So 11 inches, 0.4 tenth, 22.162 feet. And quite often folks use prisms, but there are angle gauges. You can make your own angle gauge. You can make your own Jim, your own Crusoe. Some people do use relloscopes, and occasionally people will measure it manually with a tape, just knowing the limiting distances that we have here. I can measure to a plot center from any tree. I can run a tape from any tree, right? Run that horizontal distance and determine whether the tree is in or out. And that's what we're using these tools for, prisms, for example, to minimize probably a large amount of that work. So we don't have to do that for each individual tree, right? But you should manually check borderline trees. So when viewing through a diopter prism, one of the following 3 views will be observed corresponding to one of the 3 sampling possibilities. The tree's cross-sectional area, dBH, is larger than the projected angle and thus will be sampled in. Okay, and you can go back and look at the slides when this will happen with the slide with the angle. Okay. This here is kind of what we're talking about. When the cross section of that tree at 4.5 feet is larger than the sides of the angle as these sides are diverging, whether that tree's cross section is larger or not, given the angle or the BAF, right, and its associated plot radius factor that you select in a prism, it will give you these appearances. So in this case, this tree would be in, all right? The tree's cross-sectional area, DBH, is smaller than the projected angle, and thus will not be sampled. It'll be out, okay? Notice that this prism, this piece of glass, has displaced that part of the stem beyond the remaining stem. Or the tree is in a borderline, or the tree is a borderline tree, or is in a borderline state. Thus, the projected angle is tangent to both sides of cross-sectional area DBH of the tree, or nearly tangent to where you cannot identify it truly with the prism, and you need to check it with a tape. Further work must be done to determine if the tree should be sampled. So we have our borderline tree, or the borderline state. Further work is needed to determine if this tree should be sampled, because it's too hard to tell whether that tree is in or out. This one is clearly in, this one's clearly out, because it's displaced beyond this stem. But this one is too hard, and this is a true borderline tree. I mean, to say you would have a true borderline tree, everyone, the tools, the loggers tape, the prisms that we're using would be pretty, it'd be hard to tell a tree is truly borderline, especially the tools that we're also sometimes using to establish the point. Nonetheless, though, that's what a true borderline tree would look like in a prism. Right? A true borderline tree, but many trees are going to appear to be borderline, and that's when you need to check them. And you need to check them to make sure that you're correct. So the tree on the left is included in the sample since the tree is not completely displaced when viewing through the prism. It's not completely, this part of the stem is not completely displaced, so it's in. The tree in the middle is a borderline tree and would need to be checked, and the tree on the right would not be sampled since the tree is beyond completely displaced by the diopter prism. So does horizontal point sampling result in a biased estimate of the desired dependent variable? Meaning, if we're sampling larger trees at a greater probability, what does that do to our blow-ups when we go from the trees plot to the blow-up to a per acre basis or a per track or stand basis? We should be biased, correct? But that's what's interesting. This is how we get the 10 BAF prism, the 20 BAF prism, the 5 BAF prism from sampling theory. So statistically unbiased means that across repeated random sampling, on average, the sample estimate will equal the true value. Stated differently, unbiased means that the mean of all sample estimates will equal the true value. So we want to use estimators, tools, procedures, techniques that are unbiased. It would seem that if smaller trees have less probability of being sampled and that in a sense they are being discriminated against in the selection process, that this sampling method would be biased. And you can think of it as leading to overestimates of basal area, volume, value, etc., right? Because we're sampling the larger trees, individual larger trees, more than individual smaller trees. So you would think we would overestimate volume, correct? Value, basal area, because they have larger basal areas. The larger trees have larger basal areas. it would seem that if smaller trees have less probability of being sampled, that in a sense they are being discriminated against in the selection process, that this sampling method would be biased and lead to overestimates of basal area, volume, value, etc., like I just stated. So we're going to look a little bit deeper into that. For horizontal point sampling, the probability of sampling a tree varies relative to tree size, in this case, square feet of basal area. And thus that tree's imaginary plot size varies, correct? Remember, from fixed area sampling, to determine the per acre or per tract blow up or expansion factor for a sample tree or plot, you first calculate the inverse of the plot area relative to the per unit area, whether that be acres or hectares, or the tract area, and then multiply that number by the tree attribute, volume, the dollar value. Thus, although in general we will sample larger trees when using horizontal point sampling, each large tree has a smaller blow-up factor than relatively smaller trees, because its imaginary plot is larger, so therefore it expands or blows up less into a per acre basis. If I have a larger plot, which allows me to have a greater probability of sampling that tree, okay, when I expand it to a per acre basis, it has a smaller expansion factor. Okay? That tree represents fewer trees per acre, that larger tree, because it has a smaller expansion factor, because its plot takes up a larger part of the acre. And we want that because we want to sample with a greater probability that larger diameter tree, basal area, but it has a smaller blow-up factor. So if we have a small diameter tree and it has a small plot, right, and has a low probability of being sampled with variable radius, it's going to have a large blow up because it's going to go into a per acre. That tree's imaginary plot is going to go into a per acre a lot. Okay, it's going to have a large blow up, a large expansion. Thus, each relatively large tree sampled is representative of a smaller number of trees per acre or trees within the tract. This basically reverses the bias in the selection process towards larger trees, and the overall result is an unbiased estimator. This is how we get the 10 BAF, the 20 BAF, regardless of the diameter of the tree. Because larger diameter trees have larger basal areas, but their expansion factors, how many trees per acre that tree represents, is fewer or less relative to smaller trees that have smaller basal areas. But the fact that you sample a small tree and it has a low probability implies that there must be a lot of them out there. Sampling theory would imply that. So therefore, it has a larger blow-up factor. And that's how you get the constant BAFs, the constant basal area factors. So, for example, let's assume that we have sampled two trees, a 6-inch and a 13-inch tree, using both 1/10 acre fixed plots and a BAF of 10, and that we want to determine how many trees per acre each sampled tree represents. The per acre expansion factor for the fixed area plot is simply 10, right? It's just the inverse of 1/10. 0.1 is 10. Thus, each sampled tree represents 10 trees per acre. That's the good thing about fixed radius. Okay. For whatever size plot that you're doing, you just take the inverse, and that's the number of trees represented by that tree being sampled. So on a 1/10 acre plot, each tree sampled represents 10 trees per acre. That's easy, but the basal area is not that easy. Variable radius has the advantage of that for each sampled tree, the basal area is constant. That's the BAF. So in many ways, variable radius is advantageous, right? Because BAF, basal area, is what, a 1-dimension or a 2-dimension? It's a 2-dimensional measurement, and we're often after that 3-dimensional volume or weight. So in some ways, it's advantageous in that sense, right? A lot of folks can just run a prism and estimate the basal area, or a Jim or a spiegelreloscope, and estimates of basal area was really just with no measurements, just with the prism determining visually whether that tree is in or out and counting the number of entries and then multiplying by the BAF to get the basal area per acre. And that's very efficient. Whereas with the fixed radius, you'd have to measure the diameters to get the basal area, and that's a little bit more work. When using variable radius plots, the expansion factor or blow-up factor varies by tree size and the selected angle represented by the BAF, and we've already talked about that. For a 10 BAF, for example, the plot radius factor is 2.75 feet. Thus, the plot radius for the 6-inch tree is 16.5 feet, right? 6 times the PRF, plot radius factor of 2.75. And the plot radius for the 13-inch tree is 35.75. 13 times the PRF, plot radius factor of 2.75. These plot radii correspond to imaginary plot areas of 855 square feet per acre for the 6-inch tree and 4,015 square feet for the 13-inch tree, respectively. Thus, after dividing each by 43,560 square feet per acre and inversing, the 6-inch tree represents 51 trees per acre, while the 13-inch tree represents 10.8 trees per acre. So with the 1/10, each one of those trees, because they have the same probability of being sampled, has the same blow-up, has the same number of trees per acre. And they both represent 10 trees per acre. We are saying, if they are indeed sampled, we are saying the fact that they are sampled, there are 10 other 6-inch trees out there, or there are 10 other 13-inch trees. Here, because the 6-inch tree plot is smaller, because it has a lower probability of sampling, it's smaller, it has a larger blow-up. And we're saying that the fact that it has a smaller probability of being sampled, and it's still sampled, that leads us to believe that there must be a lot of them out there, or at least a greater amount of them out there relative to a 13-inch tree. All right? So therefore, that 6-inch tree being sampled represents 51 trees per acre, while the 13-inch tree represents 10.8 trees per acre. Now, if there truly were a lot of 13-inch trees out there, you would sample a lot of them, correct? All right? So, once again, you guys, it'll give you an unbiased estimate, theoretically, okay? But think of this. Also, this is kind of why we use it. If you sample a 6-inch tree, it implies that there's probably a lot of them out there. Do you want to spend a lot of time measuring 6-inch trees? This is kind of saying, right, there's almost 5 times as many 6-inch trees than 13-inch trees. You'd want to spend your time measuring more 13-inch trees that are generally going to be more valuable, right? And yet still getting at essentially the same thing as the fixed, but measuring in a way fewer trees, because you're going to probably be spending more time measuring trees using the 1/10 than 10 BAF if there truly are more 6-inch trees out there. Does that make sense? That's why we're doing the variable radius, to help us in many ways reduce our sampling time by not measuring a lot of trees that maybe we're not necessarily interested in. Now, if we're equally interested in both of these size trees, then we probably want to do the fixed radius. And if we want to reduce sampling times, then we just use a smaller plot, like a 1/20th or a 1/50th. But here, if we're going to use a 10 BAF, we're probably more interested in spending more time measuring our larger diameter trees. So why do the smaller tree have a larger expansion or blow-up factor per acre basis? This is indicative of the fact that since the probability of sampling a 6-inch tree is less than the 13-inch tree, if a 6-inch tree is actually sampled, there must be more 6-inch trees in the stand than 13-inch trees, right? And if there's not, you're going to sample a lot of 13-inch trees. If they're equal amount, then you're going to pick that up in your sample. But that's just sampling theory, okay? So remember, inventory is an art, okay? And you have to take that into account when you're conducting your inventories. But these are tools that you will learn over time when to use a particular sampling method, what BAF to select, what fixed radius plot to select, if that's what you want to use. And we can look at this similar to what like a fixed radius. So what is the blow up? How many times can this smaller plot go into the acre as compared to the larger plot? Remember, with variable radius, point sampling, horizontal point sampling, angle gauge sampling, whatever term you want to use, larger diameter trees have larger imaginary plots relative to smaller diameter trees. And we want that. We want a greater probability of sampling this larger diameter tree than the smaller diameter tree. So if this was my forest, okay, and we just happen to have these two trees here, or we can think of it as two separate forests if you wanted, and I randomly located any point in here, or randomly located any point in here, which tree would have a greater probability of having a point eventually land in its imaginary plot area? The smaller tree or the bigger tree? Well, you should have randomly located points land in this larger tree's imaginary plot more than the smaller tree, and that's what we want. Okay, but of course this larger plot expands less into a per acre basis, into a per, whether it be tract or stand, but usually we're talking about per acre expansion factors, and then we expand to a tract. It expands less because it's bigger, so it has a smaller expansion factor to a per acre basis. This imaginary plot is smaller, so it expands more, blows up more into this per acre basis relative to this larger diameter tree. And that's, once again, you guys, kind of what I'm getting at with the unbiased estimator. That's where you get your BAFs. This is a larger basal area. This has a greater probability of being sampled, the tree, but it has a smaller expansion factor. So if you picked whatever basal area factor you picked, 10, 25, 40, if both of these trees were sampled, they would represent the same BAF. The smaller plot representing a tree with a smaller diameter can go into an acre many more times relative to the larger plot that represents a tree with a larger diameter, right? Hence, the potential bias that you would think with sampling larger trees with the greater probability is reversed. Although the probability of sampling the smaller diameter tree is less, if indeed you still sample it, right, it's got a low probability of sampling it, and I still sample it, that tells me there must be many of them out there in the stand. Now, that may not necessarily be true, or it could be true, right? That's sampling theory, everyone. That's why you need to be knowledgeable about what sampling protocol you need to select, all right? If you don't want to spend time sampling 6-inch trees, just don't put them into your population. Define your population differently, all right? Many times, though, we want to sample 6-inch trees, but if there's a lot of them out there in the stand, we don't want to spend a lot of time sampling 6-inch trees. We want to get some idea of how many are out there. That's why we use the variable radius. We want to spend our time sampling more of these trees. Okay? If we wanted to spend time equally sampling time to both size trees, potentially, then we would use a fixed. That's why, once again, you need to know your variable radius. And you can pick 10, 20, 40 BAFs such that you spend less or more time measuring particular size diameter trees. And hence the expansion factor to a per acre basis will be greater for the smaller diameter tree because its imaginary plot expands per acre. It has a greater, it expands into a per acre basis, I should say, a greater amount, right? Reversing the potential bias of sampling larger diameter trees with a greater probability. And we can see that here. So as explained in the previous section or slide, blow-up factors when using fixed area sampling is how many times the fixed area plot can occur within an acre or hectare if we're using metric, or the tract or forest if we're blowing up to something larger than an acre. So for instance, like a 1/10 acre plot can be located within an acre 10 times. It's 1/10 of an acre. Thus, how many times can a 1/10 of an acre area be established in an acre? Well, 10 times. Thus, any plot measure within that 1/10 acre plot would be multiplied by 10 to obtain per acre values. Unlike fixed area plots, though, variable radius sampling has no fixed area conceptually, and actual plots never established. However, prior to sampling each tree within a tract, or I should say, let me say that differently. However, prior to sampling, each tree within a tract has its own imaginary plot based on tree size and the angle selected, the BAF selected, the basal area factor. If that tree is sampled, any measure of that tree can be blown up to a per acre basis or tract basis by determining how many times the imaginary plot can go into an acre or that tract. It's similar to the 1/10 acre. It's just that it's not constant for every tree. The blow up or expansion factor is not constant like the fixed radius, because the variable radius has a radius that is variable, and therefore the imaginary plot area is variable, and so therefore the blow up to a per acre basis is variable. So, for example, let's assume that we use the 10 basal area factor prism projected an angle of 104.18 minutes, and we're measuring let's say an 11.5 inch tree was sampled. It was found to be in. So for a 10 BAF prism and an 11.5 inch tree, the imaginary plot has a radius of 2.75. Right, that's our plot radius factor associated with that angle. And therefore, with that 10 BAF, and you take that plot radius factor, 2.75 times the dBH, which is 11.5 inches, and that gives us a plot radius of 31.625 feet. So to determine the area of this imaginary plot, we use the area of a circle, pi r squared. Remember, we've done this, I believe, several times now. So pi times r, which is what? The plot radius factor, 2.75, times the dBH, 11.5 inches, 31.625 feet. We put that in here, and it's 3142 square feet. And before I do that, everyone, we can go back here. So remember that 2.75 is coming from here, your plot radius factor, for that angle size and that BAF of 10, your basal area factor, your angle size associated with that BAF, and the plot radius factor of 2.75, which essentially is coming back from this, okay? As you increase in size 1 inch in diameter, that tree can be an additional plot radius factor away and still be sampled. And in this case, for a 10 BAF, it's 2.75 feet. And so you can see you have your 2.75, your plot radius factor, right? And it's 11.5 inches, so it can be, in a sense, 11.5 2.75s away. And that gives you your 31.625 feet. And it can be that far away from the point and still be sampled. So how many times does this imaginary plot with the square footage of 3,142 go into an acre? Well, it's 3,142 square feet divided by 43,500 square feet per acre. That's 0.07 of an acre. And if we take that 1 divided by 0.07, it's 13.9. Thus, the fact that this tree was sampled represents that there are 13.9 11.5 inch trees per acre. So unlike the 1/10 acre, right, when we say when a tree is sampled with a 1/10 acre fixed plot, we say there's 10 trees per acre. Since we used the 10 BAF and this 11.5 inch tree was sampled, we say that leads us to believe, through sampling theory, probability theory, that there's 13.9 11.5 inch trees per acre. So for a particular basal area factor, BAF, regardless of tree size, the square feet of basal area per acre represented by any tree sampled is equal to the BAF. That's the wonderful thing about variable radius is that any tree that is sampled using a particular angle selected and thus associated basal area factor, that tree represents so many square feet of basal area per acre when you're doing horizontal point sampling. Therefore, we can get a very quick estimate of basal area, and we don't need to do any other measurement other than just shooting angles to trees, as long as we're able to determine whether a tree is truly sampled or not. That's where you get into borderline trees. Other than that, you guys, you don't have to do diameter measurements or heights or anything to get an estimate of basal area. Now, volume is different, or trees per acre is different. Okay, so then we now can say, for example, then the basal area of the 11.5 inch tree, the basal area of that individual tree is equal to our, what's this number here, everyone, right? This is what? R, Forster's constant, 0.005454154 times the dBH, 11.5 inches squared is 0.72 square feet. Remember, this constant is taking us from diameter measured in inches to area in square feet. And therefore, that's our basal area. It is area, cross-sectional area at 4.5 feet above the ground in square feet based on measuring diameter in inches at 4.5 feet. So that is 0.72 square feet. And how many times, how many trees per acre are we saying are out there with this square feet of basal area? Well, we're saying there's 13.9 of them. So, and if each one of those 13.9 trees has a basal area of 0.72 square feet, that gives us 10 square feet per acre. Given the fact that this tree was sampled using that 10 BAF prism, Jim, whatever, the fact that it was sampled using the 10 BAF tells us then there's 10 square feet per acre represented by this one sample tree. So that reverses kind of the bias, the probability of sampling larger trees. You would think it would be biased, right? That you would maybe overestimate basal area or volume. But the fact is that it kind of reverses it because you have smaller expansion factors for larger trees. Larger trees have a greater probability of being sampled. Thus, we cannot say than smaller trees. Thus, we cannot say that we believe there's a lot of them out there. If there is a lot of them out there, you'll sample a lot of them. If we sample something with a low probability and we still sample it, that believes us through sampling theory. That it leads us to infer there must be a lot of them out there. Okay, so let's say instead we are also using a 10 BAF prism. Okay, projecting a 104.18 minute angle, and a 2.5 inch tree was sampled. Now, that tree has a lower probability of being sampled than the 11.5 inch tree. Why? Because its imaginary plot is smaller. It has a radius of 2.75, our plot radius factor, okay, times 2.5 inches, which is 6.875 feet is the radius of that imaginary plot for that 2.5 inch tree. It can be 2.5 times 2.5 plot radius factors away, okay, and still be sampled. And our plot radius factor is 2.75 for this angle, or equivalently for a 10 BAF basal area factor. So you can see it as a smaller imaginary plot radius, right? So to determine the area of this imaginary plot, we use the area of a circle, very similar to what we've already done, pi r squared, pi times the radius, 6.875 feet, 148.5 square feet in that imaginary plot. And then to determine how many times the circle goes into an acre, we divide 148.5 square feet by 43,560 square feet, so 0.0034 of an acre. We divide, how many times does that go into an acre? We go 1 divided by that, it's 294.1 times. So it can expand, blow up to a much greater amount, correct, than the 11.5-inch tree. So we can think of this as the 2.5-inch tree, and this is the 11.5-inch tree. And that smaller imaginary plot blows up. It goes into an acre many more times than this larger plot, imaginary plot. And so for thus, the fact that this tree was sampled represents or leads us to infer or to believe through sampling theory, probability theory, that there are a lot of them out there, a lot of 2.5-inch trees per acre out there, that there are 294.1 2.5-inch trees per acre. Now that could be true, and it could not be true. But that's what this is leading to. We have a low probability of sampling it, and we still sample it. Well, that tells us in the probability world that there must be a lot of them out there. So for a particular basal area factor, BAF, regardless of tree size, the square feet of basal area per acre represented by any tree sampled is equal to the BAF. That's the beauty of the variable radius horizontal point sampling approach. For example, the basal area of the 2.5-inch tree is equal to what? Our Forster's constant. Okay, 0.005454,154 times the dBH in inches, 2.5 inches squared. Remember, this is taking us from diameter in inches to cross-sectional area in square feet, this constant. And we have 0.034 square feet, okay, at a height of 4.5 feet of basal area for that one individual, or for an individual 2.5-inch tree. And by the fact that we chose a 10 BAF and we sampled that 2.5-inch tree, that leads us to believe there's 294.1 2.5-inch trees out there per acre. We multiply that by the basal area of an individual 2.5-inch tree, 0.034 times 294.1, and we get 10 square feet per acre. And we'll go through and do one more example. So for example, let's assume that we use the 10 basal area factor prism. We projected this angle, right? They're kind of associated with each other. And we happen to sample a 28.5-inch tree. For a 10 BAF prism and a 28.5-inch tree, the imaginary plot has a radius of what? 2.75, our plot radius factor, times the diameter in inches, 28.5 inches, gives us 78.375 feet. And the way I think of it, you guys have to, is it can be 28.5 plot radius factors away and still be sampled because it's a large tree. To determine the area then of this imaginary plot, we use the area of a circle, pi r squared, pi times, right, the radius, 78.375 feet squared. It's 19,298 square feet. To determine how many times the circle goes into an acre, 19,298 divided by 43,560, that's 0.443 of an acre. How many times does that go into an acre? Well, 1 divided by 0.443 is 2.257 times. Thus, then, through probability theory, sampling theory, the fact that this tree was sampled represents that there are, okay, we are led to believe that there are 2.257 28.5-inch trees per acre out there. Now notice there's a large probability of sampling this tree. All right, notice that 0.443 times this, very low probability of sampling that 2.5-inch tree, and we still did. Okay. Now, there's a high probability of sampling this 28.5-inch tree, so, you know, if it, okay, there's a high probability of sampling. We were expecting to sample one, in a sense, you can think of it. So we're not confident that there's a lot of them out there, because we were expecting to sample them, right? If there are a lot of them out there, we will sample, and right, in our sample, we'll sample a lot of them out there, okay? But each individual one does not represent as many trees, probability theory-wise, as a 2.5-inch tree because we weren't expecting to sample many of them. It has such a small imaginary plot. So the fact that we sampled one there, that leads us to infer, okay, may not necessarily be true, but leads us to infer there's a lot of them out there. Okay, so we have a smaller expansion blow-up factor with this larger tree. For a particular basal area factor, in this case 10, BAF, regardless of tree size, the square feet of basal area per acre represented by any tree sampled is equal to the BAF. For example, the basal area of the 28.5 inch tree is equal to what? Our Forester's constant, 0.005454154 times what? The dBH of the tree in inches, 28.5 squared. Remember, this Forester's constant takes us from what? Diameter in inches to area, cross-sectional area, in this case, in square feet, 4.5 feet. Okay. It doesn't have to be at 4.5 feet, right? But this diameter measured in inches going to area in square feet. And then we multiply that by the diameter in inches, and we square it, right? That squared. And it gives us 4.430 square feet for that individual tree. And we were saying how many of these 28.5 inch trees with this basal area, 4.43 square feet, exist per acre. Well, we're saying there's two. We're saying that the fact that this 28.5 inch tree was sampled using the 10 BAF leads us to believe there's 2.257 of them out there, trees per acre. And then if we multiply those two numbers together, we get 10 square feet per acre. And that's the beauty of variable radius point sampling, horizontal point sampling. That any tree that is sampled represents a constant basal area per acre, constant BAF. That's your basal area factor. And this is where you need to learn to select your basal area factor given your objective. And that's what I've touched on a little bit in the fixed radius and the variable radius videos. Is through experience, everyone, you will learn. You're just starting out, but you need to put your proper amount of time in to get a base knowledge of variable radius, because it's used a lot in forestry, timber appraisals particularly, but many types of forestry, even management plans a lot. Okay, but you can hopefully tell how this could be very useful in timber appraisals and in certain kind of land acquisitions, all right, land transfers. But timber appraisals, because normally we're going after the larger, more valuable trees. Now there can be some cases where trees may be too large, and so maybe you don't necessarily want to sample those larger trees. I mean, those are very rare cases. My point is everyone know what your objective is, and then understand your population, and then kind of at least have an understanding of your population before you go sample. Right? That's why we do preliminary cruises, why we look at previous inventories. We talk to other folks familiar with that land. We talk to the landowner, private landowner, if it's an individual, right, or a family. We talk to them about the background of the site, or if we're working for a timber company, we look at the records of that site. When it was planted, what was the planting density? Okay, when was it then? When was it not? Has it been then? We can get some idea of what should be out there, and we can tailor. Now, when we actually conduct a cruise, well, it may not be exactly what we thought. All right, that's sampling theory, probability theory, but we should have some idea through experience what would be an appropriate sampling protocol, sampling approach. What would be an appropriate basal area factor if we were indeed using variable radius or horizontal point sampling? What would be an appropriate basal area factor given our objective? Do we want to sample 2.5 inch trees? If we don't want to sample 2.5 inch trees, then just don't sample them. Okay, or pick a relatively large basal area factor so that you don't sample many of the smaller trees. Now, if you want to sample a lot of, if you want to sample the smaller trees, or if you're working on a low basal area stand, then you probably want to pick like a 5 BAF, right? Or if you want to sample, right, every tree diameter in this case of equal probability, then you use fixed radius. You don't use variable radius. Variable radius is used a lot of times when you don't want equal probability. You want to sample a certain part of the stand of forest with a greater probability than another part because you want to spend more time measuring. You want to spend more activity measuring time, logistics, effort, measuring that certain part of the population. And so you need to set up your inventory protocol to help you do that. And with experience, you'll see, and I've already told you kind of some examples of when that would come about or why you would want to sample certain parts of a forest or stand more than others. And therefore, you need to define your population appropriately.